All right, it has higher frequency than radiation with a wavelength of 402 nanometers. Is that true or false? The longer the wavelength, the higher the frequency or the lower the frequency?
Lower.
The lower the frequency. So this is longer wavelength, so this has got to be lower frequency, so that's false.
The answer key said it was true.
They said A was true?
Yeah.
Okay. Yeah, it can't be true because, longer wavelength they're both moving at the same speed. And so, answer key's got to be wrong on this. But did they give an explanation?
They might have. I was looking it up as well on different websites, and they were all saying the same thing. So I thought it was
They're saying the same thing. 402 nanometers is higher frequency.
Yeah. Well, I couldn't a lot of them you have to pay to see the answer, but I saw at least a couple. Yeah, it's true since frequency and wavelength are inversely related to each other. Radiation of a shorter wavelength has a higher frequency.
Yeah, so the shorter wavelength, this should have a higher frequency because it's shorter. This is longer wavelength, so it should be lower frequency. The equation, we have this equation that relates frequency and wavelength. C is equal to mu times lambda, and the frequency times the wavelength is equal to the constant speed of light. So frequency is going to be C over lambda. So we have that. Which one would be higher or lower in energy? Would 402 nanometers be higher or lower in energy than 266? It'd be lower in energy. In 402, do you know where that is in the spectrum? Yeah, this is kind of getting. It's in the indigo violet region. Yeah, it's almost to the border of violet to ultraviolet. B, it is visible to the eye. False. It has a greater speed in a vacuum than does red light. False. Its wavelength is longer than that of X-rays. That's true. X-rays have very, very short wavelengths. X-rays have wavelengths on the order of what? The size of an atom. And so this is why X-rays are used to generate images of atoms in molecules and crystals.
A single atom, right? And there was two atoms.
Yeah. And so the reasoning goes like this, if the wavelength is too long, it's not going to see something very small. You need something comparable to the size to see it. Well, the X-rays are going to interact with the electrons. Okay, other questions?
I had some on questions about equations that were needed for some of the homework problems.
All right.
So 41 is one of them. I didn't know if we had gone over this equation or not. It's de Broglie.
I didn't go over the de Broglie. This is for light or electromagnetic radiation. Lambda is equal to C over nu. Or there are more equations than this. If we factor in energy, energy is equal to h nu, which is equal to hc over lambda. And so lambda is also equal to hc over E of the photon. You know, all these are for EM radiation. Electromagnetic radiation, we think of waves, and waves can have particle-like properties, which are called photons, but also matter can have wave properties too. For example, the electron, but not just the electron, all matter has wave properties. And it's not going to be this equation here. So it's not equal to C over frequency, and it's not equal to hc over E of the photon. When we look at matter, we're going to have the de Broglie equation. Which is lambda is equal to H over mv. Sometimes I forget these equations, but you know a way to, not that you have to memorize it, but do you know a way that you might be able to figure it out if you do forget the equation? A lot of equations come from this dimensional analysis. And so let me see if I got this one correctly. And that is, I'm going to see if I can get the correct units for lambda. Lambda should be in the units of meters. And so H is in joules times seconds. And a joule times a second is a kilogram meter squared per second squared times second. So what happens here is, okay, the units for H are going to be, well, seconds are going to cancel one of those, the denominator. And so it's going to be kilograms meter squared per second. Now, if I take this and I divide it by the mass in kilograms, then the kilograms cancel. And if I divide it by the velocity in meters per second, then one of the meters cancel and the final seconds cancel, and that leaves me with meters. So I wasn't sure if this was the right one since my memory is bad, but if you had to memorize it, which you don't have to memorize it, sometimes you can just derive it based on fundamental dimensions and units that we have. So we didn't notice like for example, a baseball. You know, the energy of a baseball that's thrown is quantized. You know, when we look at the wavelength, though, the wavelength is so short. It's so short, but that doesn't necessarily mean it has super high energy. No, it doesn't. For over here, if we have a short wavelength, let's say on the order of angstrom, then we're looking at X-rays. That's pretty high energy. But over here, we have a wavelength on the order of an angstrom. It's not like an X-ray. This is not like an X-ray coming at you. You know, in fact, the wavelengths are so short here that the next allowed one is negligibly lower and negligibly higher in energy. And so it's pretty much a continuum. So baseball, you know, if somebody throws it, you don't really see the quantization effect because this is a gigantic box. And so this is like a particle in a gigantic box, The wavelength is insignificant compared to the size of the box. Therefore, it's essentially a continuum of energies. And so this particular problem was just to show, okay, if you have a 145 gram baseball traveling at a speed of 168 kilometers per hour, you know, what is the wavelength? It's So what is the wavelength that you calculated for this?
I didn't.
You didn't calculate it? Okay. This is just one of those things, it's just the comparison. I didn't talk about this because I was running short on time, but this is like one-time calculation that we can do. Let's go ahead and calculate the wavelength of the baseball here. This is why it wasn't noticed. It's not until the box gets very small that you start to notice these things. Like an electron in an atom. An atom is a very small box. And so H is, you don't have to have this memorized either. 6.626 times 10 to the negative 34. Divided by the mass in kilograms. 0.145 kilograms. Divided by the velocity in meters per second. So this is kilometers per hour. We need to change it from kilometers per hour to meters per second. And so that's going to be 168 kilometers per hour. So sometimes the homework is used to cover other topics. I don't have time for. All right, so I'll take that. So divided by 168. Oops. Divided by 168, then I'm going to divide by 1,000. Then I'm going to times by 60 squared. All right, so the wavelength I get, lambda, for the baseball, 9.792 times 10 to the minus 35 meters. If I did the calculation correctly, what kind of light is that? Well, it's not light. If this were light, what kind of photon would this be if this were light? And so let's take a look at what kind of photon this would be. Let's double check the calculation. But the point is, the wavelength of the baseball is extremely small. And if this were light, what kind of photon would it be? If this were light, what kind of photon would it be?
I don't know if it goes beyond gamma.
Yeah,
This is wavelength in meters.
I mean,
it would be
ultra. It would be like a photon that would annihilate the world, right? You don't want to shine this photon on the Earth.
I'm going to call it ultra violet.
No,
Would it be like a supernova maybe?
No. I mean, it's just like there's a certain limit. It would be kind of interesting. But fortunately, this is not like this. So it's not like you're trying to catch the baseball and you're going to be hit with some ultra gamma radiation. It's not like that. So matter waves are a bit different there. And so matter waves, when we look at matter, the wavelength is so small it's negligible. So it doesn't really play factor. This is why people didn't notice. You know, quantum mechanics is the physics for everything, whether it's big or small. It's just these quantum effects are negligible for large bodies. So this is why classical physics is still in use. You know, when you apply quantum physics to a baseball, then the equations simplify into Newton's laws, which are classical physics. So you don't need quantum physics to model a baseball. You can just use classical physics to do that. All right, so the point of that particular homework was that there's a difference between macroscopic objects and particulate. Okay, were there other questions from the homework?
Yeah, two more that I had, like, I didn't think we had been given the equation for. 46.
Show that the uncertainty principle is not significant when applied to large objects such as automobiles. Assume that M is precisely known. Assign a reasonable value to either the uncertainty in position or the uncertainty in velocity and estimate a value of the other. All right. There are two common ways the Heisenberg equation is written. This is one of them. This is the uncertainty in the position and the uncertainty in P. P's momentum is greater than or equal to, this is the fundamental limit. The fundamental limit is h over 4 pi. There's another symbol for h, and that's h bar. And so there's a little strike through line that runs through h, and that takes into account the pi part of this. This is the other equation for this here that you'll often see. And so it's actually h bar is 2 pi. Planck's constant divided by 2 pi here. And so either h or h bar, it doesn't matter which one you use. But if we use h bar, then it's a different number. It's not 6.626. It's 6.626 divided by pi divided by 2. And so we could do that. So, you know, basically, this particular problem is, and this goes to the my philosophy on homework, and that is, or my thinking on the homework is that, you know, some of these problems you don't have to really do the calculations in detail. You could just consult the solutions guide and see how they did it, and so you just registers in your mind, okay, this is this kind of problem, and so you have some kind of idea, but it's not necessarily going to be the type of problem where you're going to be doing a lot of calculations based on it, because we're just doing estimates anyway. And so in this particular problem, you know, the thinking that I had was you just read the problem, you know, show the uncertainty is not significant when applied to large objects such as automobiles. You read the problem and then you just look at the answer. That's the kind of thing. And so that you have some kind of idea of what it is. Well, we can do this one when applied to large objects such as automobiles. So assume that M is precisely known, the mass. Okay, so how much does an automobile weigh?
200 pounds.
That's 2,000.
2,000 pounds is a very light automobile.
A ton. Yes.
Yeah, most automobiles weigh a lot more than that.
My car weighs like 800 pounds.
I think
My car is
800.
very light.
How much does your car weigh?
My car is extremely light.
Wow,
It's not even a ton.
not even a ton.
No, but
What
it's
kind of
also
car is that?
a Honda Fit. It's very small.
Yeah. Okay. Yeah.
I'm pretty sure one of my siblings could live in. They tried very hard.
Yeah, there's not much metal in those. I talked to a mechanic, and he said Hondas are built to such tight tolerances. They use a minimum amount of metal in those.
Yeah. No, it's also an older model, so it's also very.
Yeah, no, light is nice because you can save gas.
Oh yeah, no, we save a lot. I save a lot. Yes.
So 2,500 pounds. Large automobiles 4,200. My electric, I was surprised how much. I wonder how much a Tesla. Let's say Tesla.
About 1.5 to 2 tons.
So we'll just say 4,000 pounds. 2 tons. That's pretty heavy.
2 tons.
Or whatever you want to do. Should we do a small car? Probably a small car. So we'll do the Honda Fit. 2,000 pounds, let's say. So that's a math. Okay, we'll use the equation from our book. Heisenberg certainty. Two ideas leading to quantum mechanics. De Broglie. This is the de Broglie equation. U, I just use V for velocity. U for velocity doesn't really matter. P is momentum. Momentum is mass times velocity, which is energy. And then the uncertainty principle. All right, so we're going to use H over 4 pi. All right, so what did they want us to do?
Us knowing an exact M and using either delta X or delta P that's been assumed to calculate if the value is negligible or not.
Okay. To either. Okay, what we're going to do is we're going to assign a reasonable uncertainty to one and then calculate the other. All right, so first one we'll assign a reasonable uncertainty to, okay, so we have delta X times delta P is greater than or equal to H over 4 pi. When they have two versions of the equation, it's always easy to get it mixed up. So usually just memorize one version, but you don't have to memorize this. If you're taking quantum or Chem, you'd have to have it memorized. It's a very famous equation, Heisenberg. I remember Heisenberg very well because I was taking Chem at UCLA, and the professor, he gave a test. One of the questions on the test was, what is the Heisenberg uncertainty principle? And so he gave back the test, and he was very disappointed in the class because he said that, this is like general Chem 1 level stuff. And yet, I think 30% of the class didn't know what the Heisenberg uncertainty principle was. And so he was shocked. And so a lot of people didn't do so well on that test. But anyway, delta X times delta P, let's assign an uncertainty in the position. This is going to be in meters. So how much uncertainty do you want to put in the position of the automobile? Would you say, the you know the location of the automobile within, let's say, an angstrom? No. How about a meter?
Yeah, a meter stick, right?
No. Okay, maybe we eyeball it rather than measure it. If you eyeball it, what would you say about the position? You know, how far are you away from the curb or something like that? What would be reasonable? Or if it's moving, it depends on how fast do you want it to move? What velocity? Well, if it's zero, we can't go to zero, fortunately. It's got to be moving. So what velocity do you want to put to the automobile?
Meter per hour.
Well, let's do miles per hour. How fast do you want the automobile moving in miles per hour?
1 mile per hour.
1 mile
It's
per
barely
hour.
moving at all.
Who drives 1 miles per hour?
My mother.
All right. Maybe let's go a little bit faster. How about like 25 miles an hour or something?
Yeah, let's go the speed limit. How about 35 miles per hour?
35 miles an hour. All right.
Pace.
So what we're going to do is we're going to pinpoint the velocity at 35 miles per hour, and we're going to just say that there's going to be minimal error in that velocity. How fast? What would you say? Plus or minus what is the uncertainty? If you're driving 35 miles an hour and you're looking at the speedometer, what do you think that uncertainty is? Plus or minus 2 miles per hour. All right. All right, so if we're driving at 35 miles per hour, plus or minus 2 miles per hour, this is going to be our delta U for velocity. You know, and that delta U, well, the mass is going to be precisely known. And so this is going to be delta X. We're just going to leave delta X open. And then we're going to say, okay, times the mass, we're going to go with 2,000 pounds. And times the delta P of delta U of 2. Well, actually, P is going to be mass, 2,000 pounds times delta U, which would be 2 miles per hour. Now we have to get this in the right units. And so we're going to convert pounds to grams and then grams to kilograms. And so there are 453.6 grams per pound. And then 1 kilogram is equivalent to 1,000 grams. And then we'll have to go from miles per hour to meters per second. So a mile per hour to meter per second, we're going to convert miles to feet. And so 5,280 feet per mile. And then we're going to go feet to inches, 12 inches in a foot. And then we're going to go inches to centimeters, 2.54 centimeters per inch. And then we're going to go from centimeters to meters. 1 meter equal to 100 centimeters. And so that gives us meters. And then we're going to go hours to seconds. 60 minutes per hour. So we need to go 1 hour equivalent to 60 minutes. And then 1 minute equivalent to 60 seconds. And so that should give us meters per second. All right, so this is going to be 2,000 times 2 times 453.6 divided by 1,000 times 5280 times 12 times 2.54 divided by 100 divided by 60 divided by 60. Okay, that gives me 811.11. And then what I'm going to do is I'm going to invert it and multiply by h. So I'll invert this times 6.626 times 10 to the negative 34, and divided by 4. Divided by pi, 3.14. And so I calculated delta x equal to 6.5 times 10 to the minus 6.50 times 10 to the minus 38 meters. All right. What this is of course the uncertainty is going to be bigger than this because of our measuring and that kind of stuff, but this is the fundamental limit. You know, you can't know the position with less uncertainty than this. Does that make sense? And so this is such a small number that that Heisenberg's uncertainty principle is not significant. What's significant is our measurement inaccuracies. So if we try to do the measurement, our uncertainty is going to be much, much bigger because of the tools that we use to measure it aren't going to be this precise. I mean, this is way, way smaller than an atom. You can't pinpoint that. Even the atoms are vibrating. But I guess you can get the average position. All right, if we do the same thing, let's say, if we do the same thing and we say a car is moving at 35 miles an hour, if a car is moving at 35 miles an hour, what's a reasonable uncertainty? Well, if you're eyeballing its position, then in that second, it's going to be difficult to pinpoint, right? And so it's going to be tough to do. Tough to do. So the thing is, this is another type of problem. I mean, this is more, if I were to assign something like this, I mean, this is just plug and chug kind of thing. Just make sure the units work out. You know? And so this type of problem, as well as the de Broglie wavelength. De Broglie wavelength, you might get a calculation like that to see if you can get the units correct. But, you can just read the question and then look at the answer for these. We don't really calculate the Broglie wavelength so much, except for an electron. I don't know if I gave that. There's a homework problem which you calculate the wavelength of an electron moving at 1/10 the speed of light. Did you see that problem? And the wavelength was about the size of an atom. That was. Okay, other questions?
I was wondering something else about Z. What are we talking about, like Z or Z effective?
Z or Z effective, you need to know if we look at the hydrogen atom, what's the nuclear charge in the hydrogen atom? +1. That's called Z. So if an electron were in a 1s orbital, what Z effective would it see? I mean, what effective nuclear charge would it observe? +1. And so Z effective is equal to +1. what if we move this electron to a 2s orbital? If we move it to a 2s orbital, here, what Z effective would it be? Plus 1. Yeah, also plus 1. What if we move it to a 2p? It's only got one electron. If we move it to 2p, what would the Z effective be?
Plus 1. We only have one.
Right. It would also be plus 1. If we go to lithium, Z is plus 3. And so one thing you should know is what happens to the 1s orbital. It moves down in energy. What happens to the size of the 1s orbital? It gets smaller. And so lithium is going to have 2 electrons in the 1s. And then all the orbitals are smaller, including the 2s. The 2s orbital is smaller than that 2s. In fact, lithium should be a smaller atom, except it's not smaller than hydrogen. It's smaller than other ones. But anyway, going back to this, now we have a choice. We can put the electron in the 2s, the third electron, or the 2p. Which one should I put it in, the 2s or the 2p, and why? I should put it in the 2s. That would be the lowest energy. Why is that? I mean, why is the 2s lower in energy than the 2p? You're right, off-valve says to fill the 2s before the 2p, but
Also because it's closer.
it's closer to the nucleus? Well, both the 2s and the 2p have the same effective distance, from the radial distribution function. The most probable distance is the same.
But 2s is more penetrating.
2s is more penetrating. And therefore, 2s is going to have a higher Z effective than the 2p. The 2p, if I put it in the 2p, it's going to be a lower Z effective. And so the Z effective on 2s is greater than the Z effective because it's more penetrating. And therefore, it's going to see more of the nuclear charge. These two 1s electrons block this. And so the effective nuclear charge is around 1. It's a little bit higher than 1. Because these two positive charges are canceled by these two negative charges here, essentially. Leaving a Z effective of plus 1, but this Z effective is a little greater. This Z effective is a little lower. You need to know Z effective in that sense, what it does to the size.
So it's correlated with how shielded.
Right, how shielded and how penetrating. This is all penetration. This is going to see if more of the nucleus because this 2s electron is more penetrating, less shielded than the 2p. The 2p is less penetrating, more shielded. And the shielding is going to occur from these inner shell electrons, the 1s2. And so Z effective is the whole reason why we get the splitting. And if everything just had one electron, there's no reduction in Z. In fact, did I assign that homework problem?
Does what you said about Z effective stay true for all elements, or is there an exception to the rule where the charge can be higher
No,
despite the shielding? Okay.
it's true for all. There's a very very simple equation for calculating Z effective or estimating Z effective.
Oh boy, it's the equation of testing.
That, I thought I had assigned it, but maybe I did not. Yeah, sorry.
Right before it. Basic calculations of this before 8 was at 8 a.m.
Okay, I'm good with it.
The 2023 Tesla model. See what it says. Whereas the number is showing electrons. Whereas you use the atomic number as the number is showing electrons.
Surprise. This is too oversimplified, this equation.
I was gonna say, that seems very simple.
Yeah. The equation, actually, this is for MCAT. I would think the MCAT, for the medical exam, they would want to know it a little bit more. I mean, this is way oversimplified.
But that's for check assembly, right?
Check it.
Well, anyway, this is the way we calculate Z effective. Z effective is equal to Z minus the shielding. And here they oversimplify it by saying the shielding is only due to core electrons. In this case, it would work. But when we get to, let's say, something like this, then it doesn't work. Quite so well. It is true that the core electrons shield 1 for 1. So for every core electron, we lose one of the positive charges. That's what that equation is saying there. However, what about these 2s electrons? Will these 2s electrons shield the 2p? Yes, they do, but they aren't very effective shielders. So we apply a factor to these electrons here, and that factor is about 0.3. Where the factor here would be 1. These 100% shield, these about 30% shield. That's it. And there's an equation in the homework.
Does that scale downwards as you go higher?
Oh, no, it's always the same.
It's always
Yeah, inner shell electrons shield 100%. Same shell electrons are about 30% shielders. So this equation's oversimplified. So let's look at another one here. This one was also oversimplified. We had a better equation in the book. I don't know where it went. This is called Slater's rule. And Slater is the one who came up with the shielding scheme. So all he did was apply certain factors. So inner shell electrons shield 100%. Electrons in the same group shield 35%, except the 1s, which is shielding at 30%. Electrons within an n-1 group shield 85%. Electrons within the n-2 or lower group shield 100%. And so the more inside, what we do is we just kind of come up with some simple generalizations of this. But the inner shell electrons are very effective shielders. And then as you start building up shells, then they become less and less effective because the shells kind of grow big, very big, and therefore 85%. And then same shell, it depends on how big it is. Although this doesn't quite, there must be some repulsions going on with that. And these are Slater's rules. And I thought we had it in the homework, but maybe not. And so this is the scheme here for shielding. And it goes on. The nice thing about Slater's rule is very, very easy calculation, and the numbers come out okay. We can use quantum mechanics to dictate or calculate what Z effective is, but this, we don't have to use any of the heavy math of quantum to figure it out. And so what is the effective nuclear charge experienced by a valence D electron in copper? Valence D, we don't really call those valence, those are inner. Okay.
Copper has a special charge at 1410 4s1. I think that was it. That is for copper. Right?
Oh, okay, no wonder. I couldn't find it. I couldn't find it because I'm in the wrong chapter mentally. Slater's rule, this is in chapter 9. We're going to see Z effective again in chapter 9 here. And so chapter 9, number 69, I assigned this as a homework problem here, so you can do the Slater's rule calculation for shielding. Okay. But for right now, it's what causes the splitting for the multi-electron, and this is why the Bohr model failed. I mean, one of the reasons, and multiple reasons. All right, other questions? Uh-huh. I didn't get very far on 9. We'll just do 7 and 8. Yeah, just homework for 7 and 8 or 2. There are some chapter 9 problems on that last test, but very few. I think I only included like 3 or 4. But it's close enough. We'll just skip 9. All right, anything else?
I had some questions about practice exams. I
Okay.
don't want to take too much time. I can always ask Sylvie during office hours, but one of them was 1 on the practice exam.
Okay, take a look.
This one I was confused because it included PV work in the equation, but it wasn't, like, there's no change going on in this equation. It's PE plus EK plus PV equals what? And I'm confused how the work can happen when there's no change.
Okay. Number 1 was that?
Yeah, number 1.
This is, there was a diagram I had written up earlier, beginning. Let's say we're looking at U, and this is U initial, let's say. And then there's U final. Let's make this an endothermic reaction. So we're going from lower internal energy to higher internal energy. And then we have delta U. Delta U we know the equation for. Everybody should know. Delta U is equal to Q plus W. That's one of them. There are multiple equations, for delta U. But what is U? We never do delta U as U final minus U initial, do we? No. And the problem with doing that is what?
Potential energy is not absolute.
Yeah, the potential energy is what's going to give us problems. And so what we're going to do is, if we look at U initial is the total energy, which is equal to the sum of the potential energy plus the kinetic energy. And so that would be it. But we don't calculate the potential energy, or we could try to estimate it. But, this is potential energy, that's kinetic energy. This is a different symbol for kinetic energy, E sub K. But what's this PV thing here that's going on? PV. PV work is P delta V, though, right? And so if we're looking at H, let's go with H initial and H final. And then we have delta H. Delta H is going to equal delta U
Minus P delta V.
Well, minus the work. And if we do P delta V work, then it's going to equal delta U plus P delta V, or minus a minus P delta V. This is another equation that we could use. But do we do H final minus H initial? Why not?
Potential energy is not absolute.
Yeah, same problem with this. And so we can, all I'm going to do is I'm going to use this equation for delta H here. Like this. And so this is called a change. And these are the absolute enthalpies here. And so we're going to have a change in the absolute enthalpies of this. Well, the absolute enthalpy initial is going to equal U initial plus, now this is kind of weird, it's going to be PV initial. And when we think about it, the pressure stays constant here, but when we think about it, U is the energy, the total energy, but what we're going to do is we're going to also define the PV state. The PV state is also energy too. This is going to be atmospheres times liters. Liters atmosphere is also energy. And so there's going to be a certain PV state that this is going to be. There could be no change in the PV state, but there could also be a change in the PV state. And so this is going to be U final plus the PV state final. That's PV final. And so what we do is we see, what is the pressure and the volume initial, and then what is the pressure volume final. And then by comparing the pressure volume initial and pressure volume final, we can figure out how much work is done, that is P delta V. And so this first thing is weird because we never calculate it, right? But this is the absolute enthalpy. The definition of enthalpy is this. This is the definition of enthalpy, which is going to be U plus PV. Or it's equal to the potential energy total plus the kinetic energy total plus PV. Our book uses E sub K for kinetic energy. And so this is what this is. This is the definition of absolute enthalpy. That's how absolute enthalpy is defined. Absolute internal energy is defined as this. Absolute enthalpy is defined as this. The difference is enthalpy, we got to see what the PV state is so we can see how the system interacts with the surroundings. For delta U and U, we don't care how the system interacts with the surroundings. Here we do care because we need to maintain constant pressure. And so question number one is, this is the definition of the H. And not delta H, the absolute enthalpy, which we never calculate anyway, but.
Honestly, I don't think we could calculate it because we would have to
We-
find the
yeah.
absolute potential energy.
Right.
And
So
that
we
would take way too long.
Right, but as far as definitions go, that's the definition, even though we don't calculate it.
So what is PV? Is that just pressure times volume?
This is a pressure volume state, so we need to know what pressure volume state it is at the beginning, and then we can compare it at the end to see if there's any change in the pressure volume state. Is there a change in the pressure volume state, then that's going to involve energy, because that means the volume changed, let's say, went up or down, that kind of thing. And so it's just to otherwise we don't know if there's a change. If you don't pay attention to the pressure volume, then how can you tell if there's any change? If you ignore it, you can't ignore it because, some gases will have to expand, some gases will have to contract in the reaction. And so we need to know the pressure volume state. And pressure volume is actually an energy state. This would be like energy state, an extra energy term here. So if we're looking at the total energy, then we got to look at the pressure volume state in addition in this case, because it can change and that could lead to changes in delta H. Well, it's kind of weird, but it's just the pressure volume state is just an energy term. So if this is confusing, you can still go. Okay.
Sort of italic font is not working. Let me put it back in a second.
This is the equation of state. And so we need to know, because the energy depends on that particular thing. And so we have to know what it is at the beginning and know what it is at the end. So this is a PV, this is Boyle's. These are some simple gas laws. So there's some stuff written about it. Doesn't quite make sense, but it's kind of weird. But we need to know what the PV state is initial and the PV state is final in order to do delta H. And so this is why it has to be included in there. PV is just another energy term. So it's all relative, it's all relative. So this is its relative energy here. When we do that, well, we do it quantitatively, we calculate our delta H's, the difference. So that's quantitative.
So is like the heat of combustion.
Enthalpy, the change in enthalpy, it's not just combustion. The change in enthalpy is for anything. Yeah, not just the heat. We have delta H of vaporization, which is the enthalpy of vaporization. We have delta H of condensation, delta H of fusion, delta H of this, delta H of that. Delta H is just the energy. This is the way delta H is the change in energy. The change in energy factoring in how it interacts with the surroundings. That is, does it blow up against the surroundings or does it contract and the surroundings doesn't work? And so delta H is the change in energy of anything. It could be a physical process, it could be a chemical process. If it's delta H of combustion, then we're looking at the total energy change in the combustion, but we have to factor in how it interacts with the surroundings. Is the surroundings going to play a role in energy exchange there? And in order to determine if the surroundings plays a role in energy exchange there, then we need to know is there a volume change. In order to determine that, we have to know what the volume is initial and what the volume is final. When we look at a delta U, does the delta U tell us if there was any change in the volume? No. And so what we have to do is we have to see how it's going to interact with the surroundings in this case here. And so we need to know in order to figure out the volume, we need to know what it was initially and what it was final. And so this is called an equation of state. PV, what was its initial pressure volume state? What is its final pressure volume state? If the pressure didn't change, then we say the pressure is constant. And if the volume changed, then we say, oh, there was a volume change. And if there's a volume change, that's an energy change. And that energy change is part of this thermodynamics equation here. And so we need to know what the pressure volume state is. And so this is the absolute. This is the absolute potential energy. This is the absolute kinetic energy. The absolute kinetic energy is easy. Potential energy is hard. Absolute PV state, easy. This is pressure times the volume is going to be whatever joules that is initially. And then we look if there was a change final. But this is just another energy term that we add. You know, when we look at the total energy, what is the total energy? We just keep adding the energy terms there to get it. But in this case, you know, this is just looking at the system here. We look at the system and the surroundings. In that sense, that's one way of thinking about it. I mean, it's just a term, another energy term that's added on there, and that's the definition of enthalpy, absolute enthalpy. We never calculate the absolute enthalpy. And when we do like enthalpy of combustion, enthalpy of fusion, whatever, those are changes in enthalpy. And so it's not always clear what somebody's talking about. Are they talking about the absolute enthalpy? Are they talking about a change in enthalpy, delta H versus H? Since people don't really talk about absolute enthalpies because we don't calculate those, then that's it. But in order to do the equations of thermodynamics, you need to know the equation for this because there's some things that you have to calculate based on the absolute, not the change. And so this is the, maybe you don't, the relevance isn't here right now, but you know, if you're taking, let's say, the next thermodynamics class, then you need to know the absolute, this, and the change, this. Okay, so, you know, enthalpy is defined in different ways. Let's see what Wikipedia.
Why that is a spot computer.
We see Wikipedia will give the absolute definitions. Do you see? These are all absolute definitions, not the delta. Because we start off with the absolute and then work on. When I did U, I started off with the absolute and then I went to delta U. That's typically what's done. I didn't do it for delta H because we derived delta H from delta U. It's easier that way, and plus, you know, but this is the definition of H. H is equal to U, the absolute internal energy, plus its pressure volume state. So they use lowercase p. But don't worry about it so much. You know, something that you should know later. There's another one. There's another two. The internal energy up there, I don't know why they didn't write it, but Helmholtz and then the Gibbs and more on top of that. So that particular problem, at least the equation that I gave was this. And so I'm thinking, can you work backwards from this to what it must have been, you know, initial and final? And so most of them I worked forward here, like U. And so this was one I was thinking maybe you could work backwards and get it. Not an easy question. All right, other questions?
Another thing is the lecture that you did, like for the blue structure lab, like the SP3, like all that stuff. Will that be on the exam?
Hybridization.
Yeah, hybridization. Yes, I want to put that on the test. So hybrid orbitals, just some hybrids. What you should know are the atomic orbitals.
Should I know the shapes?
And so let's. I have this animation here we can watch for hybridization. One thing is this. Do you see this? What do we call this diagram here?
Energy diagram. Energy. Delta energy. No.
We don't energy diagram. If somebody said, "Okay, draw an energy diagram," you'd go, "Well, which energy diagram are you talking about?"
Quantum atomic energy.
No, if somebody said draw the quantum atomic energy thing, it's still no. There's a name for it. What is the name for it?
Atomic orbital energy level.
Yeah, if somebody said draw the atomic orbital energy level diagram, then this would be it, right? However, these aren't all the atomic orbitals, but you go, no, this is all of them because of the Schrodinger's equation. We get all of them here, and so I can just keep going. 1s, 2s, 2p, 3s, 3p, 4s, 3p, 4p. I can just keep going, right? But then what happens is these atomic orbitals can combine to form hybrid atomic orbitals. And so what are the hybrid atomic orbitals? So let's take a look. This is like
hybrid orbitals are formed by a mixing of the hydrogen-like s, p, and d orbitals that characterize a free atom. The three p orbitals are directed along the x, y, and z axes. When we mix an s and a px orbital, we produce two hybrid orbitals called sp pointed in opposite directions along the x-axis. Mixing of an s with the px and py orbitals produces three equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes, which contain most of the electron density in the orbital. These are used in bonding to other atoms. Mixing of the s with all three p orbitals results in formation of four equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron.
the minor lobes usually aren't shown.
Let's apply the concept of hybridization to ammonia. Here is the Lewis structure for ammonia. There are four electron pairs in the nitrogen valence orbitals. We know that an ammonia molecule has a pyramidal shape. This shape can be explained by assuming that the central nitrogen atom employs sp3 hybrid orbitals. The unshared electron pair occupies the fourth sp3 hybrid orbital.
All right, so that's basically what we're doing today. So what do you need to know for hybrid orbitals? You should know that there's going to be, right now, there are three types of hybrid orbitals that we have covered so far, and those are the SP. Yeah, SP, SP2, SP3. Those are the three types. And so how do those form? Well, we need to hybridize an S and a P. And so there's no hybrid orbitals in the first shell. In the first shell, we can't because there's no p orbitals in the first shell. But in the second shell, we have p orbitals. We have the 2s and the 2p. In the third shell, we have p orbitals, fourth shell. So any shell higher than 2 can hybridize. So what does an s orbital look like? An s orbital looks like this. And a p orbital, what does that look like? Yeah, looks like that. And so here we have an s orbital and a p orbital. And what we're going to do is we're going to hybridize those. We also have two unhybridized orbitals, and those would be unhybridized p orbitals. And so what I'm going to do is I'm going to draw those here. So there's going to be an unhybridized p orbital here. And then there's going to be one that comes straight out of the board and goes straight in. That'll be unhybridized p as well. So if I take the purple ones, I'm going to get two new orbitals oriented 180 degrees apart. This. And I should draw these bigger. And so those are my new two sp hybrid orbitals, and those are going to be 50-50. They're going to be halfway in between in terms of energy here. And so I'll have one sp and another sp here. And then I'm going to have my two unhybridized p orbitals here. And so one of the p orbitals will be in the plane, and the other p orbital will stick out of the plane here and go in. And so we have those. So that's sp hybridization here. And so we have to modify our energy level diagram. And so we'll still have our 1s orbital here. That's unhybridized. But now we have these new hybrid orbitals. We'll call it the 2sp, the 2sp, the 2p, and the 2p here. The next hybrid orbital is sp2. So what we're going to do is we're going to hybridize the 2s and two of the p orbitals. We'll just take these two p orbitals that lie in the plane here. That's going to leave one p orbital unhybridized. And that p orbital will have stick out of the plane. And so this p orbital here, let's just draw the line differentiate between the two p orbitals. In the video, it showed the hybridization, then showed the separation. But when we do sp2, we're going to get three sp2 orbitals in a trigonal planar arrangement. So I take this purple, and then that leaves me with one unhybridized p orbital here. So the atomic orbital energy level diagram looks a little bit different. It's going to look like this. Now, the energy is going to be 2/3 of the way up to p, but not quite there. And so that one unhybridized p orbital will be here. So this is an sp2, this is an sp2, and this is sp2. So we form three sp2 orbitals. Okay. And then we'll have one unhybridized p orbital that sticks out like this. There are two ways of drawing this. One is with p orbital perpendicular to the plane. The other is with the p orbital in the plane, the page. So this will be sp2, and then I'll have one sp2 that sticks out of the plane, and then one sp2 that sticks into the plane. And then we could put the p orbital in profile here. This would be an unhybridized p orbital here. And so this is looking at it from the top down. This is looking at it from side view. So this is the top view. I call this the top view. And this I call the side view. The side view because we could see the p orbital in profile of this. Okay, this would be the 1s. And so we have to modify our atomic orbital energy level diagram when we have hybrid. And what we get are these new hybrid orbitals. These new hybrid orbitals are mixing of the original orbitals there to make new atomic orbitals. And so it's not just the s, the p, the d, the f orbitals, but we also have the hybrid atomic orbitals too. Now the hybrid atomic orbitals, this is actually in chapter 11. But I'd like you to know these are some additional atomic orbitals that you should know. The last one is the sp3 here. And in this case, we're going to hybridize all three of the p orbitals here. So if we look at the unhybridized orbitals, we're going to have the 2s orbital here, and then a p orbital here, a p orbital here, and a p orbital here. So we have those three. And then when we hybridize it, we're going to generate 4 equivalent orbitals. The 4 equivalent orbitals, we draw one in the plane and another in the plane at a 109 angle. And then one sticks out of the plane, also at a 109 angle. One sticks in. So in other words, we're going to draw a tetrahedral arrangement of sp3 orbitals. And this is what we never draw the minor lobe because otherwise the drawing gets a little bit too complex. But they're like p orbitals with one lobe and it's lopsided. One lobe big and the other lobe tiny. And so we'll just draw the big lobes here. Okay, and then the diagram's going to look like this. These are my sp3 set of orbitals, and then I have my 1s, which is unhybridized. Okay. This is just in the second shell. So what we have to do is we have to modify our atomic orbital energy level diagram to account for the hybridization of the orbitals. So to get more practice with this, that's what we're going to do for today's lab. We're going to practice these. Are there any other questions to be answered?
So in the original drawing, all of the p orbitals have 2 lobes.
Yeah.
They have 2 lobes in the sp3.
They do. All of the sp3 orbitals have 2 lobes, and the other lobe is going to be very small.
E3 hybrid pair occupies the 4th group orbital chain. Pairs in a nitrogen valenization. Let's apply the constant.
Or let's take it like, you see this sp3 orbital that comes up here? On the opposite side of that is the minor lobe. So each of these has a minor lobe. It's like a p orbital, but it's a lopsided p orbital. Most of the time, we completely ignore the minor lobe. In fact, all the time, we completely ignore the minor lobe because volume doesn't occur. That's negative amplitude. And so when we look at this, do you see the minor lobe? These are their 4 sp3 orbitals, but they didn't bother drawing the minor lobe here. Should be a minor lobe here, here. This lobe is color-coded blue because that's where the lone pair goes, but these are for bonding here. So what are all the shapes of the atomic orbital. S look like what? Spheres. All of them look like spheres. P, like a dumbbell. D, most of the D's look like four-leaf clovers, except for one. One of the D's has this weird P-like shape with a hula hoop. But four of them look like this, and one of them look like that. F look like what? F are going to be chopped up into more lobes, so you don't have to worry about an F, etc. But in addition to these atomic orbitals, you should know the SP. What's the SP atomic orbital look like? Well, we have two of them, and it's going to look like this. And then we're going to have unhybridized p orbitals here. This is one, and this is another one. Two unhybridized p orbitals. But the SP orbitals here and here. Those are two separate orbitals. Kind of looks like a p orbital, but p orbital, this is one orbital with two lobes. The SP is just a single lobe, as I draw on it here. And you should know that. SP2, trigonal planar. This is a linear arrangement. SP2 is trigonal planar with one unhybridized P perpendicular. This would be the top view. And then SP3, which would be a tetrahedral arrangement. Of orbitals. So these are all our atomic orbitals here. But these ones, you know, we had to do a little bit of modification. The little bit of modification is this. What we did was we took our standard orbitals, which is the quantum mechanics of it, and then there were two approaches to handling more complicated species. In atoms, this is never a problem. In atoms, all the orbitals are unhybridized. Why did we have to hybridize? In atoms, we only have unhybridized atomic orbitals. In molecules, we can have unhybridized and hybridized. And the primary reason for hybridizing was what? To minimize repulsion. And these are atomic orbitals. So we stop here. And then we generate something called valence bond theory. Valence bond theory just says that a bond is equal to an overlap of atomic orbitals. Versus the other approach. And so this is what we call the simplified version of bonding. The simplified version is not the most accurate version. What the most accurate version is this. We take these unhybridized and hybridized atomic orbitals, and then we do an LCAO. LCAO stands for linear combination of atomic orbitals. With LCAO, then we generate new orbitals called molecular orbitals, or MO theory. Molecular orbital, which we call MO. Atomic orbitals are called AOs theory. And so valence bond theory versus molecular orbital theory, these aren't competing. These are complementary. In a way. It's just that MO theory is difficult. Calculations. This is easy. No calculations really involved. This is easy, but limited. And so we could do valence bond theory with pencil and paper. You can't do valence MO theory with pencil and paper. But limited. No energies. Here, this is difficult, but we can get a lot more information from this. More accurate. Well, the calculations are difficult, and so that could decrease the accuracy of this. But if we could do these calculations without making too many assumptions or simplifications, then it would be accurate. This is the more accurate in terms of energies, etc. And so we'd like to do everything with MO theory, but it's hard. MO theory, what we see are we have a whole new set of orbitals. And so what orbitals have we had so far? Well, we've had S, P, D, F, G, etc. And sp3, sp, sp2, sp3. And then when we go over here to MO theory, we're going to have sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2p, actually sigma 2p, let's go. Sigma 2p, pi 2p, pi 2p, etc. And so we're going to have a whole new set of orbitals to memorize. And so, but first we want to memorize all the atomic orbitals. And since the hybrid atomic orbitals are atomic orbitals, then I was going to include those on the exam. So if you want to see more about the hybrid atomic orbitals, check chapter 11 for that. All right, so let's go ahead and analyze. In our lab, now this lab is going to be done totally different than what's on the report sheet, so just include this into your lab notebook. All right, so we're going to start off with NH3 was the example here. And so since we're dealing with like shapes, so we can come up with a Lewis structure here. The actual shape of this molecule is trigonal pyramidal because it has 4 groups of electrons. If we have 4 groups of electrons, then to minimize repulsions, we want to adopt a tetrahedral geometry like this. And so the electrons adopt the tetrahedral geometry. But when we look at the molecular geometry just is of the bonded atoms. The Heisenberg uncertainty principle says we're not going to pinpoint those electrons up here, the lone pair. And so what we see is we can pinpoint the atoms. We see a trigonal pyramidal shape. And so that's what we did. And so we're going to do one extra thing for this, or a couple of extra things. And that is, one, we're going to draw the atomic orbital energy level diagram for nitrogen. Okay, nitrogen in this is going to be, did I already do this? No? Okay, nitrogen is going to be 1s, 2s, 2p. All right, how many electrons does nitrogen have? Now, the number of electrons can change depending on what the formal charge is. The formal charge on nitrogen is this nitrogen structure is 0. So if it's 0, then it's got 7 electrons. Is that right?
Yes.
Okay, let's go. 7 electrons. 1, 2, 3, 4, 5, 6, 7. So this is what we expect the atomic orbital energy level diagram to look like for nitrogen. But in this case, we know that nitrogen is hybridized. What's the hybridization on it? sp3. It's tetrahedral. So, tetrahedral electron geometry. And so this is going to be sp3 hybridized. And so let's redraw the atomic orbital energy level diagram for that. And so this is going to be 1s. Now I'm going to take the 2s and 3 2p's and then hybridize them to come up with 4 new orbitals. Those 4 new orbitals are going to be called the sp3 orbitals. And I could put the n or I could leave it off. I could put the n here, so it's a 2 sp3. But we have 4 of them. I'll just leave it off for right now. Okay, now how do I fill it? I'm going to fill it based on what I see over there. I see 1 lone pair, and then I'm going to have 4 bonds to it. Okay, then I'm going to look at the other atoms. What's the other atom that we have? So this is nitrogen's atomic orbital energy level diagram with the sp3 hybridization. The other atom we have is hydrogen. Hydrogen's easy because hydrogen just has the 1s. There's no hybridization there, it's just 1s. Okay, I should draw the spin down. Maybe I'll draw that spin down. And so what I'm going to show here is I'm going to show that hydrogen is going to come in with its 1s orbital here and bond. And then another hydrogen 1s is going to come in here and bond here. Another hydrogen 1s is going to come in here and bond here. I'm not going to show all, I guess I could show all 3 hydrogens over here. Well, over here, nitrogen is going to come in and bond here. The hydrogen, and I could just repeat that 2 times. All right, now I want to know what the shapes of these orbitals look like. And so what I'm going to do is I'm going to draw nitrogen here, and I'm going to draw my 4 sp3 orbitals. So I'm going to have 1 sp3 orbital coming up, 1 sp3 orbital going down at a 109 angle here, 1 sp3 orbital coming out, and 1 sp3 orbital coming in. Now, one of these sp3 orbitals is going to have a lone pair, so we'll make that up at the top here. The other one will have a single electron here, and a single electron here. And then the hydrogens are going to come in here with their 1s orbital. So I'll just draw a 1s orbital. We know it's spherical. And so that's my hydrogen 1s orbital, and that's going to have one electron here. And so in valence bond theory, a bond is the overlap of atomic orbitals. So I have a 1s orbital overlapping with an sp3 orbital. What that does is it concentrates the electron cloud between the two nuclei, and that's what holds the atoms together. Is this increased probability density in the internuclear region, creating a bond. And so this is called an ssp3 bond, or ssp3 sigma bond, because of where the overlap occurs. So we'll talk about that later when we get to the other the chapter on it. But right now, this is kind of what we want to do. We just kind of want to visualize what's happening with the atomic orbitals here and how the atomic orbitals are overlapping. This is valence bond theory. Atomic orbitals and the overlap of atomic orbitals create bonds. So this is the additional stuff I want you to do for this. There's not enough room to do this on the report sheet, so you would do it. Okay, so we'll do another one here. We'll do carbonyl chloride. CO double bond O is called a carbonyl group in organic chemistry. So we have a C double bond O, the carbonyl functional group. And there's two chlorines on here, so this is why they call it carbonyl chloride. Or phosgene. Phosgene is one of those toxic gases that we use in World War I. So if we look at carbonyl chloride, we can do the Lewis structure for this. There are different ways we can do the Lewis structure. One is we can save a lot of time and just, we know that chlorine has 7 valence electrons. And so this would be it here, carbonyl chloride. What's the shape of this molecule? Trigonal planar. So what we need is we need a trigonal planar set of orbitals. Is there a trigonal planar set of atomic orbitals? Yes, there is a trigonal planar set of atomic orbitals. What are they?
The NH3. Wait, no, it's not NH.
sp2. This has got to be sp2 hybridized. But it's all right. What we're going to do is we're going to start off with the unhybridized first for the central atom, carbon here. And so what is the unhybridized for carbon? It would be 1s, 2, 2s, 2, 2p, 2. That would be unhybridized. And then what we're going to do is we're going to hybridize it to sp2 hybridization. sp2 hybridization is we're going to have our 1s, and then we're going to have three sp2 orbitals and one unhybridized p orbital, like this. Now we fill it based on the Lewis structure, and so there are going to be 2 electrons in the 1s inner shell, core shell. Now, what do? Do I put 1 lone pair in an sp2 and 2 singles? Is that correct? So, in other words, take a look at carbon. Are there any lone pairs on carbon? There are no lone pairs on carbon. There are only bonding pairs. So there is no lone pair here. And so this is what it's going to look like. There aren't any lone pairs, and I got 4 valence electrons, so I got to do it like that. So that takes care of carbon. All right. Now I'm going to go to oxygen. So oxygen is, okay, what's the arrangement of electrons here? When I look at the arrangement of electrons in the oxygen, I see how many groups? I see 1, 2, 3 groups. If I have 3 groups, 2 lone pairs and 1 double bond, what geometry will they adopt to minimize repulsions? Trigonal planar. And so what I see is a trigonal planar. This is electron geometry. You know, this is all molecular. Molecular is just looking at the atoms. But when I look at the electron geometry, it's trigonal planar, which tells me the oxygen must be hybridized. It's got to be hybridized too. So when I look at oxygen, unhybridized, what is it? And so unhybridized, it's going to be 1s2, 2s2, 2p, 3. But we see that it's got to be sp2 hybridized based on the Lewis structure. And so 1s2 stays the same, it's unhybridized. But if it's sp2, I'm going to get 3 sp2 orbitals and 1 unhybridized p orbital. Then I look, is there a formal charge on the oxygen? I mean, in other words, I count the number of electrons based on formal charge. Oxygen has how many electrons that belong to it? Counting formal charge. Counting formal charge, we split these evenly, so that's 1, 2, 3, 4, 5, 6. There's 0 formal charge, it's got 6 valence electrons. So we took care of 2 here. I mean, these are core. We need 6 valence electrons. Valence electrons is just looking at the outermost shell. And so there's 6 here. 1, 2, 3. Where should I put number 4? Should I pair it or put it up here? Okay. 4, where should I put number 5? I'll pair it again. Where should I put number 6? Number 6 is going to go up here. Because why? I have 2 lone pairs on the oxygen, and then I have a double bond, or I need to form a bond. Yeah. All right, now let's do chlorine. Chlorine is going to be 1s2, 2s2, 2p6, 3s2, 3p. Okay, how many electrons does chlorine have? 1, 2, 3, 4, 5, 6, 7 that belong to it by formal charge. So I need 7 here. So that's 1, 2, 3, 4, 5, 6, 7. So I'm 1 short of filling the 3rd shell. But chlorine really wants that extra electron. But anyway, getting back to this, we have to be careful. We have to be careful not to confuse valence electrons with total electrons. So oftentimes, what people do with Lewis structures and with these is just to look at the valence and ignore the core. Okay, we're looking at the total number of electrons. If we switch to valence, then we have to be careful that we don't get the numbers mixed up. All right. Now, chlorine's a bigger atom. So the repulsions might not be as great in the 3rd shell as it is in the 2nd shell. And so many books, what they do is they don't hybridize it. They won't hybridize chlorine. But what we're going to do is we're just going to hybridize everything. Because how do you know when to hybridize and when not to hybridize? And so what we're going to do is we're just going to err on the side of hybridization here. As we get more experience, because this is a mix of theory. Actually, we haven't had a break, have we? Theory and we'll have a break right after this. And factual knowledge. Here, we're just going to hybridize it. So if we have 4 groups of electrons, 3 lone pairs and a single bond, what geometry should it adopt to minimize the repulsions? Tetrahedral. Tetrahedral is what hybridization? sp3. So we're going to hybridize chlorine as sp3. We're either going to stop here or hybridize it. We'll go ahead and hybridize it. And so nothing happens to the core. This is why a lot of people ignore the core electrons, because the 1s doesn't change, the 2s doesn't change, the 2p doesn't change. And so when we hybridize this, the only thing is we're going to hybridize the valence shell electrons. And that is, we're no longer going to be s and p, we're going to be sp3. So we're going to get 4 equivalent sp3 orbitals. And since this is in the 3rd shell, we'll call it 3sp3. So those are our 4 equivalent 3sp3 electrons. Now, how should I fill these? Well, I should have 3 lone pairs and 1 bond. So that's what I'm going to have here. So what's going to happen is this. One chlorine is going to come in here and single bond with this. And so this is going to be a chlorine sp3. Another chlorine is going to come in here with an sp3 and single bond here. And then the oxygen is going to come in here and double bond. Okay, on the oxygen, we're going to have an sp2 come in here and double bond, and a P on oxygen. And actually, the sp2 and the P combined will make the double bond. And so oxygen comes in here and bonds in 2 spots. So that can be shown over here. Carbon would come in here and bond in 2 spots. The sp2 on carbon is going to bond here, and the P on carbon is going to be bond here. Although I'm going to have to do something with the spins because they're all mixed up now. And then for chlorine, carbon's going to come in here and bond to this sp3. And so carbon sp2 comes in here and bonds to the sp3 here. And so that's the bonding. And so finally, what we're going to do is we're going to try and attempt to draw this. Because we know the shapes of these atomic orbitals. So what I'm going to do is I'm going to draw the sp2 like this. And then that means the p orbital is going to be oriented like this. I'm going to draw the p orbital in profile. And so this is what I call the side view of sp2. And the side view is we're going to have an sp2 here, sp2 here, sp2 here, and then one unhybridized p. And if I look at it, I have 1 electron in each orbital. So 1 electron here, 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 and then 1 electron in the p unhybridized here. Now, what I'll do here is I'm going to bond this to the oxygen first. And so the oxygen is also going to be sp2. So the sp2 on oxygen should be a little bit smaller since it has a little higher Z effective. And so the sp2 on oxygen. Now I'm going to put oxygen spin down. I put it spin up over there because I wasn't thinking ahead. But now, try to correct that. There are going to be 2 lone pairs. So this is sp2 here, this is sp2 here. And so these sp2 lone pairs can minimize repulsion by being 120 apart. And so this is part one of the double bond. It's the sp2 overlap. Part 2 of the double bond is here. There's going to be, this is side view also, there's going to be an unhybridized p orbital on oxygen. Now, these are probability boundaries, but they extend. And so we're going to get overlap above and below the plane. And so this is called a bond as well. We have different names for these. So, for example, this one is called an sp2 sigma bond. sp2 sigma bond. Sigma refers to the electron cloud being in the internuclear axis. So if I draw an axis or line between the 2 nuclei, the overlap is here. And then I have a pi bond. A pi bond is when I have overlap above and below or outside the internuclear axis. So the internuclear axis is here, but for the p's, there's a node there. And so we're going to have overlap here and here. And so when we do the clouds, there's going to be increased cloud density here and here. This is the overlap. This is not a triple bond, because these overlapping p's, these are just 2 atomic orbitals. 2 atomic orbitals make 1 bond. And then I have overlap here in this region here. Okay, then I'm going to have my chlorine. So one of the chlorines I'm going to draw here, I'm going to have an sp3. The sp3 on chlorine should be big because that's in the next shell. And so this is going to be sp3, big, next shell. And then I'm going to make 3 more. 1 in the plane, which is going to have a lone pair. 1 coming out of the plane, which is going to have a lone pair. And 1 going into the plane, which is going to have a lone pair here. And so this is sp3, this is sp3, this is sp3 here. Okay, and then I'm going to have a chlorine in the back. I'm going to try to draw it, but it's going to be difficult. draw it small to show it's further away. So there's going to be 3 lone pairs on the chlorine in the back. So this is what I call the side view. Then I can rotate this to get the top view. So let's go ahead and rotate this to get the top view. So I'm going to take this and rotate it. Now, the thing is this. If there wasn't this PP, what I call a pi bond, then this free rotation about bond. I can rotate the atoms and it won't destroy the overlap. However, if I try to rotate a double bond, it doesn't rotate. So let's hold the carbon steady, fixed, and then try to rotate the oxygen. If I try to rotate the oxygen, it'll break the bond here. It'll have to break the bond because I'm going to lose that overlap. It won't break this bond. And so sigma bonds can spin. They freely rotate, but pi bonds cannot spin. And so looking at it from the top view, I'm going to have carbon here. I'll have oxygen here, like this. And the carbon was sp2 hybridized. The oxygen is sp2 hybridized. Oxygen's orbital should be a little smaller. Okay, and then we're going to have this is the sp2, what we call the sigma bond. And then we're going to have the pp pi bond. Here, to show the pp pi bond, I'll draw the overlap so it doesn't interfere with there. So we usually draw 2 lines like this kind of thing. And we're just looking at the top orbital here, the top lobe. The bottom lobe is going to be getting superimposed here. Those are overlapping as well. And then the chlorines are going to come in here. Chlorine sp3 is quite big. This is in the next shell. It's getting harder and harder to draw these, so just kind of draw it as close as you can. 3 lone pairs there. Again, chlorine's sp3 is big. When we draw a tetrahedral, it's always 2 in the plane, and then 1 coming out, and then 1 going in. So we end up something like that. So this would be the top view. This would be the side view. Okay, then we're done with this one. Both. Unfortunately. All right, so why don't you try the next one? Or, next one will be SOCl2, thionyl chloride. The other one was carbonyl, thiosulfur, so thionyl. You can take a break. It was like